Yeah, I'd like to introduce Victoria Schleis, who will talk about tropical Quiver Grassmannians.
Yeah, thank you for inviting me. Thank you for having me here. Today I'll tell you something about tropical animals of Grassmannians. Everything I'm telling you about today has been developed in joint and ongoing work with Giulia Iezzi. Let's get started. I wanted to start out this talk by telling you what Quiver Grassmannians are. I know there are plenty of people in the audience who know that, but I also know that there are people who don't, and it gives me the chance to introduce some examples that I want to talk about. So, start talking about Quiver Grassmannians. To define a Quiver Grassmannian, I first have to tell you what a quiver is. And a quiver is an object that everyone here, I'm sure, has seen and loves. A quiver is a directed graph. And I'm going to denote the vertex set by V, the arrows by A, and I have a source and a target map for each of my arrows. And in terms of examples, we are going to consider examples today. One of these examples is the A3 quiver, which is just essentially a chain of vertices where you have a map from each arrow linearly oriented. The next quiver we are going to consider is a quiver we have already seen in Mario's talk earlier today, the Chronica quiver, which is you have two vertices and two arrows between them. And the last quiver we are going to look at is a diamond-shaped quiver like this. So from my examples, you already see that for quivers, we allow pretty much all kinds of nastiness in our graph theory. We allow to have parallel edges, we allow to have loops, and these things all have meanings. So now from this combinatorial object to get to something algebraic, what we do is we associate algebraic information to this combinatorial data we have here. So a quiver representation R is an assignment of vector spaces to my vertices and linear maps between those vector spaces to my arrows. F alpha from R source of alpha to R target of alpha for all alpha in a linear map.
Victoria?
Yes.
What are S and T?
Source and target map. So these associate to each arrow a source vertex and a target vertex.
You require it's there's a directed path from source to target or something.
No, it's one arrow. Each arrow has a source.
I think he might want you to write S colon.
Okay, sure. S is from A to B and T is from A to B. And this is the source map. And this is the target map. Okay, so to each of my arrows, I have an associated linear map. And to each of my vertices, I have an associated vector space. And for the purposes of today, I'm going to assume that my vector spaces are all algebraically closed and of characteristic 0. And I am also going to assume, and this is important for many of the theorems, but I'm also going to assume that all of them have the same dimension, which is not important for the theorems. It just makes the notation less messy. dim or vi equals dim rvj. So in our examples, the examples I'm going to consider are, I associate C4 to each of my vertices for the A3 quiver, and the maps I'm going to consider are identity maps. Now, I'm going to do very similar things for all of my examples here, but you'll see that these things tropically will turn out to be different things. So I'm going to associate the Puiseux series over C to the 2 to this vertex, and the same to the other vertex on here. With identity maps. And on the last quiver, I'm going to associate C4s again and identity maps to all of mine here. Now, the quiver representations give you some kind of rule in which linear spaces have to be contained inside of each other, and the linear spaces that now the linear subspaces that now satisfy these conditions imposed by the quiver are what we want to study. These are called quiver subrepresentations. So, a quiver subrepresentation R is an assignment of subspaces in V to all of my vector spaces associated to my vertices, and such that they satisfy the conditions imposed by the linear maps, so that if alpha of n of the source of my arrow alpha is contained inside of n of the target of alpha. So these subspaces have to be contained inside of each other under application of these linear maps imposed by the quiver. Now, the Quiver Grassmannian is the parameter space or moduli space of these objects, and it's a projective variety, a multi-projective variety. The Quiver Grassmannian of a representation R, and I dimension vector D is the set of all n subrepresentations of R, such that the dimension of each of my vertices, of the subspace assigned at each of my vertices, is the dimension imposed by this dimension vector here. And now you can realize this as a subvariety of multi-projectiveness. And choose the dimension 1 minus 1, and so on. You have this product of projective spaces that each of the vertices live in, because each of the vertices span a Grassmannian, and this just gives additional, this imposes additional conditions on this space of products of Grassmannians. Now, you may ask yourself, why should you care about these kind of constructions? Why should you care about these kind of space? Now, multiple different ways you can look at these things. One way that I like personally is this allows you to describe a lot of combinatorial relations of linear spaces in space. So this allows you to give different, to impose different settings here. So for instance, if we impose the dimension vector 1, 2, and 3 here, what this diagram here tells you, just tells you that you have a space of dimension 1 that is contained inside of a space of dimension 2, that is contained inside of a space of dimension 3. So this is just, this quiver Grassmannian associated to this is just the flag variety. But it also allows you some more flexibility. So for instance, if we look at the picture at the bottom here, and we do something very similar, we can parameterize points that are contained inside of two separate lines that don't necessarily have anything to do with each other, but are contained inside of a common plane. And of course, now you can do far more different settings. Essentially, everything you can describe using linear maps, you can study the parameter space of using Quiver Grassmannians. From an algebraic geometry perspective, Quiver Grassmannians are interesting because they cut out a large amount of interesting algebraic varieties. Namely, they cut out all projective varieties if you use the correct representation. And this representation that cuts out all projective varieties is not necessarily a very nice one, but there are many classes of projective varieties that are cut out by much nicer looking Quiver Grassmannians, where you can use the combinatorics of this Quiver Grassmannian to study the geometry of the variety. Now, and the thing I want to do is I want to construct tropical analogues of this. So what I really want to do is I really want to substitute here my vector spaces by ground sets. I want to substitute my linear subsets by tropical linear spaces over these ground sets. And I want to find a suitable analog of what a linear map is supposed to be so that I can have I can parameterize tropical objects that satisfy some conditions imposed by linear relations on them. To construct a tropical analog, I think the first guess one could probably make that I would have made at first naively is what I could do is I could tropicalize the Quiver Grassmannian. And this space turns out to be a tropical variety that parameterizes tropicalizations of linear spaces that satisfy these conditions imposed by linear maps. However, it does not parameterize everything imposed, every matroidal, every tropical linear space that comes from a matroid, because not every tropical linear space is the tropicalization of a linear space. So this parameterizes tropicalizations. Spaces contained inside of each other under linear maps. Not further, if you want to compute these things using a computer algebra system, these things are very hard to compute because you get very difficult equations very quickly. So your computer fails after ambient dimension 4, usually. So the approach that we tried to use was we tried to do this more structurally and really work with the quiver and do this replacement that I told you about before. So we replace, in our tropical analog now, we replace the ambient space by ground sets. And we replace the subspaces by tropical linear spaces of the correct dimension. Consider tropical spaces. As subspaces. Now, the thing I need to tell you about still to construct a tropical version of a quiver representation or quiver subrepresentation is I need to tell you what linear maps are supposed to be. And from this perspective of assigning ground sets to the vertices, you can already have a glimpse of what these linear maps might turn out to be if they are nice structurally. And that is, it's just maps of sets that satisfy certain conditions. So let's fix our setting. We consider a map F for each of these arrows that goes from one ground set to the ground plane itself. Now one may try to study what happens with matroids under these sets. What a reasonable assumption would be is that one needs to generalize what it means to be a morphism of matroids to the setting of valuated matroids and impose having a morphism of matroids as the condition of being contained inside of each other. So we often have this quotient condition. So we want to impose that we have some kind of pre-image of the matroid associated to this one, so to the -1 of mu, and we want this to be contained inside of the evaluated matroid mu, and matroidally, this is the same as taking a matroid quotient. Now, to define this matroid quotient, I first need to tell you what this pre-image matroid of a matroid mu is supposed to be. So if F is a map of such a space, we can define the induced matroid F to the -1 of mu to be the following valuation function on bases. So F to the -1 of mu of a set S is equal to the valuation of the image of the set F under the set S under the map F. And now you have to check that this defines a valuated matroid, and it does. Now, from a paper by Brand, Yu and Zhang, we know how to express this quotient for valuated matroids.
There's a T in Brent.
Yeah. Oh, yes. Sorry. Thank you. We have that F to the -1 of mu is a quotient of mu is equivalent to F to the -1 of mu. So that, that for all bases A in the bases of the underlying matroid f to the minus 1 of n, and the basis b of the underlying matroid n of mu, and all a in a set minus b, there exists a b in b set minus a, such that f to the mu of a plus f to the plus mu of b is less than or equal to f to the minus 1 of mu of a set minus a union b plus mu of b set minus b. So that we have some kind of Brooker condition that these quotients here satisfy.
So M and N are mu and mu.
M and N are the underlying matroids of mu.
Oh, I see.
So underlying matroid mu, and this same but for mu. Now let us think a bit about what types of maps these maps describe here. So these maps you can use to describe projection maps by allowing an additional set, by allowing maps to a loop that you introduce to the ground set. If we add an additional loop to this ground set, we can use this to describe projection maps. And we can use it to describe things like permutations of basis elements, which correspond to symmetries on your tropical linear space. And we can also use this to describe contractions, which correspond to essentially mapping two different coordinate directions into one. Contractions, i.e. mapping coordinates onto each other. One thing this definition does not allow you to do is it does not allow you to characterize things like translations of tropical linear spaces. But there is an easy fix to that, and that is to introduce a second component to this map that allows you to translate, to shift each of the grounded elements in the direction you want to shift it in. So the way we fix this is we take our definition of map here, and we assign a second coordinate here, namely a coordinate r, which then is going to be our translation factor in each coordinate direction.
Why do you want to allow translation?
Because it gives us more flexibility what we can describe. If I take a matrix and I multiply it with a linear space, I can use this to describe translations as well.
Can I ask a question?
Sure.
In the classical setting, the instance relation is imposed on the image,
Yes.
but here it's on the inverse. So how do I understand that difference?
So one thing that happens that you'll figure out when you study these things is that on the tropical matroidal side, you reverse all the arrows in your quiver representation. This essentially corresponds to the fact that the tropical linear spaces we consider are covariant to the space that we are in. So we reverse all the arrows, and this is a remnant of that. So we can't describe translations of tropical linear space, but if we impose an additional coordinate to this map, we can. Now, how does this change the induced matroid? This just means here we have to take F1 here, and we put each of my elements of my set. I sum up these additional translation factors. So in a tropical linear space, this will really just correspond to shifting everything by the valuation of, in the direction xi by the valuation of I. Now this approach allows us to describe many things, but on the algebraic side, the picture is somehow richer.
Victor?
Yeah.
So, or confused again about this translation. Shouldn't this be somehow just multiplying with diagonal matrices?
Yes, it's multiplying with diagonal matrices which don't have just ones on the diagonal.
Okay, so in the beginning you don't allow that?
No, in the beginning you don't allow that because you just have maps of ground sets.
What does this times R mean?
This times R is the new thing that we added to that. This times R is this allowing R.
Okay,
This is the
translation.
this is just for the translation. So another approach from the algebraic picture that we could take is we could, instead of trying to consider maps of sets, we could try fixing coordinates of our vector spaces, describing the arrows as matrices, and seeing what happens under this different characterization of the setting. What we're going to do now. Are there any questions up to this point? Well, any more questions, I should say. So two, fix the coordinates of each of the vector spaces associated to the vertex in the classical picture, obtain a matrix on the arrows, take the valuation of that matrix, see what happens in that picture. In our examples up here, one thing we could do is here we could just take the identity matrices with the FL picture, so we could put this on top of my arrows. But for instance, for the Kronecker quiver, we're going to take a different matrix. So on top, we are just going to take the identity matrix. And on the bottom, we're going to take the matrix 1 and 1 plus 2. This still evaluates to the identity matrix, but we will soon see that having two different maps in here can cause problems. Fix coordinates on the algebraic side, obtain matrices for arrows, take valuations of these matrices. Structurally, there's a problem with this approach, and the problem is that multiplying a tropical linear space pointwise with a matrix does not necessarily give you a tropical linear space anymore. So for instance, if you wanted to see an example, you could consider the matrix 1, 1, 0, 0, 1, 0, 0, 0, 1, take its valuation and multiply it with the classical tropical line. And what you would get is you would get kind of a cut-off tropical line where you're missing a ray that goes off in the direction y. But it also has an advantage, and the advantage is that we have equations. And from our discussion yesterday evening, I think we all agree that having equations is very good for trying to study things using tropical geometry or any kind of hyperfield. And these equations for the Quiver Grassmannian using matrices are by Oliver and Thorsten Beist, and they go as follows. The Quiver equations are each array alpha, where we assume that we have fixed matrix A alpha for the arrow. And for I in N choose ds alpha minus 1, it's alpha minus 1. And j in d minus 1 has to go in here. Sorry. And choose dt alpha plus 1. We have a set of Quiver equations that is essentially augmented by the matrix of the map that defines it. So we have P alpha n equal the sum over j in n without I, and I in j, the sine, now some sine function, which is the classical sine function that you would come up with, but tropically it makes no difference, so I'm not going to write it down. J I j a alpha ij p I union j p j. So this is really just the standard picture of the Quiver equations, where we go over all possible things we can add to my set I and things I can take from my set j, where I augment it by the matrix A alpha here. So if I wanted to just describe the usual Grassmannian, I would take an identity matrix here from n to itself. If I want to obtain the incidence Quiver relations that cut out the flag variety, I would take an identity matrix here with different, going from with spaces of a different rank here, and I can now obtain complicated things as well, complicated sets of equations. So the Quiver Grassmannian set-wise is the space cut out by all the Quiver relations for each of the arrows and all of the Quiver relations for each of the vertices. Q, T, R, the P, B vertices and intersected with whatever surface is cut out by these Quiver relations over here, alpha or alpha in my arrows. say here is if you're from an algebraic geometric perspective, these equations might not be nice for you because they may not result in the same scheme structure on the Quiver Grassmannian that you would usually get if you were to study it. At least that's what the Quiver people tell me, Oliver.
That's precisely the scheme structure.
Okay,
That's,
then, okay,
I
maybe,
mean, there's a difference. How you define the Quiver Grassmannian is as a variety, but it gains scheme structure by realizing it as fiber of a universal Quiver
Yes.
Grassmannian wave parameter space. And the scheme structure is precisely recognized.
Okay.
basis.
the Quiver people told me that they were very worried about it not doing that, so,
I mean, that's proven in this short paper.
okay. So this is as a variety. Now, one thing that we can do is we can look at these equations and look at what they cut out from. So we can, as a tropical parameter space, define the Quiver Grassmannian. Is the tropical free variety. Cut out by these Flickr equations. So QDR R D is the intersection over P and my vertices, trop of P V, and now we intersect this with the A, with the alpha in my A P. And it turns out that this space actually parametrizes what we wanted. So this space actually parametrizes tropical linear spaces contained inside of each other under matrix multiplication. Stop. And let me write it just down for a shorter example. So for a quiver where I have two vertices, one arrow in between, the arrow has matrix A alpha, and I have valuated matroids, mu assigned here, mu assigned here. Then I have mu times mu is in the Grassmannian associated to this matrix A alpha and the correct dimensions, so rank mu, rank mu. If and only if tropicalization or valuation of A alpha tropical times space valuation of A alpha tropical times trop mu is contained inside of trop. Now, if we wanted to make this a statement about the associated valuated matroids, we have to be very cautious, right? Because of the example I showed you earlier, where you have tropical linear spaces that after matrix multiplication are not tropical linear spaces anymore, so they don't correspond to valuated matroids anymore. But what we showed is that this construction that we had done in the beginning that defines this for sets is exactly a subcase of this case here, and the subcase where things are nice from a matroid theory type point of view. So further, every morphism of valuated matroids can be represented by a matrix in F such that F from every map of ground sets N union 0 to union 0 times R can be represented by a matrix M such that F from mu to mu is a morphism of valuated matroids if and only if the picture of the tropical linear spaces under this map are of the under this matrix multiplication is contained. And F tropical times trop mu is contained inside mu. And we can characterize every nice tropical linear map, so every matrix that has that this is always a tropical linear space as such a matrix that comes from a map of ground sets to R. And so in this subcase, where these matrices are of a nice form, we also have a statement on valuated matroids. In this the condition here, so mu times mu is in the Quiver Grassmannian if and only if F is a morphism of valuated matroids. Now I told you about two different tropical analogues of Quiver Grassmannians. And a natural question here now is to ask, when do these things coincide? When do these things not coincide? So to ask about representability of these concepts. And that's what I'll try to spend my last 10 minutes or so of this talk talking about. And the brief summary of what I'm going to tell you is that representability gets really bad really, really quickly once you start introducing multiple different maps to your setting. Yeah, that's okay. So we say that something is realizable if it is the tropicalization of an algebraic object instead of just a valuated matroid. And for those of you that don't know, just because my two tropical linear spaces are realizable, that doesn't mean that they are realizable inside of each other under such a linear map. So in the case of where we just had a Grassmannian, we have non-realizable examples. From n equals 7. And Chris, Maddie, and Leon proved that in the flag variety case, these examples already start to show up and you have ambient dimension 6. For flag varieties, n equals 6 already suffices. And in our setting, we actually get far worse than this. So for Quiver Grassmannians, we have two different numbers. First, n equals 3 is for arbitrary valuated fields.
Here, non-realizable means unrealizable or given field.
Yes. for arbitrary valuated matroids.
Fixed field.
And for if we have a non-trivial valuation on on the field that we come from, then already n equals 2 subspaces. N equals 2 for non-trivial valuations. And the examples that are bad are the examples that have accompanied us throughout the talk. For n equals 2, the example where things break is the Konica quiver. If you're a quiver theorist, this is not very surprising to you that this quiver is bad news because it's the smallest quiver where you have infinite representation classes. So this is a counterexample for many things in quiver theory. So for fields with non-trivial valuation, we can consider this over here, where we have the, for our example here, the field of Poisson series over C. And we have the maps here that we assigned earlier today. So we have the identity map up top and the identity map where we add a T here. And now you can pretty immediately compute from the equations that you can read off from this picture that QGR of this thing is just the points. Whereas the tropicalization forgets that these maps, the valuation map forgets that these two maps are different. And that results in you having a one-dimensional space.
One dimension vector 1, 1. What's the dimension vector?
My dimension vector is 1, 1. So I'm considering one-dimensional subspaces in this two-dimensional space. Otherwise, you don't have equations. So the Quiver Grassmannians 2 points here, and the Quiver Gaussian is the line between the between the valuation of these 2 points. So it's a nice example that you can still compute by hand. However, when you want to compute counter examples for over a field with trivial valuation, you need to get a bit more crafty and need a bit more bigger examples. So in that case, Macaulay 2 and GFN are your friends. And you can take the
It's really about rational points, not tropicalizing over the field. Well, but maybe
so sorry. Fields with non-trivial valuation, yes, over trivially valued field. We take the diamond-shaped quiver here. So in our example, we take support with the trivial valuation. We take the identity matrices on all of my arrows, and we still obtain just going to identity matrices here. And using M2 and GFAN, we obtain that the dimension of the quiver Gaussian is 12, whereas the dimension of the Quiver Grassmannian is only 10. So these two spaces can never be equal. And one can now use a trick that I learned from Oliver to break down this example into an example over ground set size 3 by using the fact that you can write every matroid over on 4 elements as a quotient of a matroid over a set of 2 elements and matroid over a set of 3 elements. And then you can write this down as a huge giant quiver and obtain a counterexample for type 3 using the exact same computations here. I'm not going to write it on the board because this quiver has, I think, 24 vertices and more arrows. So I don't think it would fit, but this is the counterexample we used to show this for n equals 3. Now let me finish this talk by talking a little bit about future directions and questions that are still open. So on the algebraic geometric side, one can show that it doesn't matter which coordinates I choose for my vector spaces and which matrices I obtain the same fiber, I obtain the same variety. But this is a priori really not clear in the tropical setting. So if I have two different question is, if I have two different coordinate choices and two different presentations of the same quiver representation by different matrices, do the quiver Grassmannians coincide? Where do they coincide? Do they not coincide at all? Do they have some kind of map between them? If you have an answer, I would like to hear it.
That's a sure no.
I think it's a no. I think it's a no.
But obviously no, I would say.
Then let me draft that down like this. How do the corresponding quiver Grassmannians relate? And what kind of information can I get from a quiver Grassmannian about the quiver Grassmannian associated to it? So which kind of information can I learn about this tropical variety from the kind of tropical pre-variety that it lives in the setting? So let me stop here. Are there any questions?
You mentioned earlier this theorem that classically every protected variety is a quiver Grassmannian. Is there any hope of a tropical analog of such a theorem?
Well, I mean, I think in a way, yes, and in a way, no. Using the Grassmannian structure, kind of obviously not, right? Because the Grassmannian, you have some pre-varieties that contain these tropical varieties. So, but I don't think this is like, this would be in any way. And of course, if you just tropicalize the quiver Grassmannian associated to the then tropical variety, to the ideal that gives you your tropical variety, you would just get a tropical variety this way. But the question is there any more information in the quiver Grassmannian associated to it? I couldn't tell you. Yes.
So if I just take a one arrow and I take a point from the quiver Grassmannian, so is the image tropical linear space the induction by the bipartite graph weighted by the matrix?
I don't know. I wouldn't think so, but I don't know. Yes.
Do you have any special keyboard Grassmannian which has some good combinatorial model? I mean, such like phylogenic trees and the Grassmannian Rn. Do you have any some?
Not at this. Yes.
So in that example of the Kronecker quiver that you were telling us, the tropical quiver is the same quiver, but the identity matrix is in both arrows, right? And then the Dressian is that line that you described there.
Yes.
You said that the classical quiver is 2 points and the tropical quiver is the line.
No, the classical Quiver Grassmannian is 2 points. Yes.
Yeah, sorry. And you said, well, the points in the middle cannot be lifted to a point in the Grassmannian, but if you choose different classical matrices that tropicalize to the identity as well, can you realize the points in the middle of the segment? Maybe not with those exact 2 matrices that you have there, but different matrices that start like 1 plus and then keys afterward.
I can do that.
All of them are realizable. All the points in the middle of the segment.
I think I could choose matrices such that they all read. Yes.
Sorry, it was a silly question because I don't know any tropical geometry. But there's a polynomial that sometimes is interesting where you take the Euler characteristic of the Quiver Grassmannian, and you encode which dimension vector you chose by writing down a polynomial with the monomial given by the dimensions. And this gives you a polynomial as you vary over the dimension vectors. Is there something analogous you can do in tropical geometry? Like, is there Euler characteristic type constructions that you build this polynomial?
I don't know. I think, Oliver, did you guys study that for the hyperfield case? I think you had, Manuel presented something about Euler characteristics in this setting as well. But maybe you have something to say about that.
In very special cases where there's a representation, I mean, if so so-called bindings, so particular representations of Tinken quivers, simply less Tinken quivers. The Euler characteristic of the classical Grassmannian over C corresponds to very particular points in this tropical quiver Grassmannians, which are coordinate points. So it becomes nice if you do the whole story of the Bresler hyperfield, then these are close features. So there's something, but it's very complicated.
And so in that case, there's like a close algebra relationship between this polynomial.
Yeah, precisely. You can recover structure, for instance, of cluster algebras by looking at certain points over the cluster hyperfield, which somehow is a tropical hyperfield just with 0 and infinity. And there you have a certain topology, it just takes a closed point, which are the points at infinity. By the way, it's also on the valuated.
Any more questions?
Well, thank Victoria again.